Hi, everyone. Welcome to chapter 11. In this chapter, we are going to be discussing probability. Let's begin with chapter 11, section 1. So we are going to discuss today basic concepts of probability. So here we're going to be defining probability. We are going to start looking at the types of probability that we have and how to solve distinct probability examples. So let's get started. In this section, we are going to be learning about basic terminology in the language of probability. We are going to be working with simple problems involving, there's both theoretical and empirical probability. So we are going to be looking at these two types of probability. Understand the law of large numbers. So there exists a law of large numbers, which is also defined as the law of averages. We are going to be talking about how to find particular probabilities related to flower colors as described by Mendel in his genetics research. So we also in biology, probabilities are also applied, and we see that in Mendel's genetic research examples. Determine the odds in favor of an event and the odds against. So we will be talking about how odds and favors odds in favor or odds against applied to our probability questions. So let's define probability. The definition of probability is the study of probability is concerned with random phenomena. Even though we cannot be certain whether a given result will occur, we often obtain a good measure of its likelihood or a probability. So what it does, it gives us a good measure or a likelihood of an event. That is a probability. In a study of probability, any observation or measurement of a random phenomenon is called an experiment. So we are going to perform probability on an experiment. The possible results of an experiment are called outcomes. That's the definition. The possible outcomes, the possible results are called outcomes in an experiment. And the set of all possible outcomes is called the sample space. Usually we are interested in some particular collection of possible samples or possible outcomes. Any subsets of those samples is called an event. Okay, so an event is something that is a subset. So an event is a subset of a sample. So we can have multiple events going on an experiment. Let's look at the first example. We want to find the probability when tossing a coin. Let's have a single fair coin, so only one coin is tossed. Find the probability that it will land heads up. So let's look at the sample space. What are your options? What are your options when flipping a coin? You can have heads or tails. So two options, and we wish to select one option. So we have one out of two choices. That tells me that's 1/2. Let's the sample space S be defined as heads or tails, and the event is finding heads. So we are specifying what we're trying to look for, and that's heads. The probability of the event, the probability of landing heads, it's 1/2 because we have one out of two choices. So 1/2 is the answer. So since no coin flipping was actually involved, the desired probability was obtained theoretically. So this example of flipping a coin, because we actually did not flip a coin, it's actually a theoretical. There's two types. There's the theoretical and there's also the empirical. Okay, so far we've talked about the theoretical because we're not actually performing the experiment. We're just taking the sample space and then selecting it by chance. Let's look at this theoretical probability formula. If all the outcomes in the sample space S are equally likely and E is an event within the sample space, then the theoretical probability of the event E is given by the formula. So this E was a subset. That subset was heads. So we were looking at the probability of landing a head that is one subset of my heads or tails. So the probability of the event occurring is equal to the number of favorable outcomes, N of E, over the total number of outcomes, N of S. So remember that N is a cardinality. In this case, how many values of E do we have? How many values of S do we have? The total number of values that are favorable on the top divided by the total number of outcomes. Now, let's look at the next example. A cup is flipped 100 times. It will land on its side. So it will land on its side 84 times. On the bottom, it will land on the bottom 6 times, and on the top 10 times. The total number of times was 100. So this 100 is my sample space. How many times did you do the experiment? You did it 100 times. So you're looking for, find the probability it would land on the top. So we're looking for the number of favorable over the total sample space. So the favorable was, okay, how many times it landed on the top divided by the total. So the landed on the top was 10 times, right? It says right here, you landed on the top 10 times over 100. That would be the probability of getting a top. You can also reduce that probability to 1/10. 10 over 100 is the same as 1/10. So there it is. You're looking for a probability that it will reach the top, that the cup will land on the top. That's 10 times over 100. That tells me 1/10. So then we want to ask ourselves, is this experimental or empirical probability? So this example, it's actually an experimental or empirical. Why? Because you're actually flipping it 100 times. You're actually doing the experiment on it. And then you're looking at, this one shows up 84 times, this one shows up 6 times and 10. They're not equally likely. So the probability is not equally likely. So it's not theoretical. It is actually experimental. It depends on the experiment, right? So let's write that down. Let's look at the definition of an empirical probability formula. If E is an event that may happen when an experiment is performed, then the empirical probability of the event is given by the number of times the event E occurred divided by the number of times the experiment was performed. So on here, the last example, it was performed 100 times. You flip the cup 100 times, and the number of times that it landed on the top was 10 times. That was the probability of landing on the top. But if we wanted to find the ones to the side, well, that was 84 over 100, right? Because we saw that it landed 84 times on the side, 84 over 100, where we can also reduce. They're both divisible by 20. So we have 84 divided by 20 gives us, well, not exactly by 20. Let's reduce it first by 2. So if we reduce it by 2, we get 42 over 50, but this can also be reduced by 2, 21 over 25. And 21 over 25 is my solution. Okay. So then what we have is 21 over 25. Alrighty, so let's continue. There are 2,000, oops, I don't want to show the answer. They are 2,598,960 possible hands in poker. If there are 36 possible ways to have a straight flush, find the probability being dealt with a straight flush. So it's already telling you, you have the ones in favor of 36 out of your total. So you're looking for the probability of a straight flush. Will be the number of successes or the number of times it occurred divided by the total amount, which is 2,598,960. You're gonna do this on your calculator when you plug it in. And it's gonna be very small. Look at the probability of this. Very small. The probability is very small. Okay. And that is an example of how many outcomes that we have. Okay. And these are also not equally likely. We have to do an experiment. So this one was, again, the number of, this would be an experimental type of probability. Let's look at the next one. Finding the probability of a resident's age range. So according to the United States Census projection for 2020, there are in a country about 56.52 million people aged over 65 and over, and 275.618 million under 65. If a person were randomly selected from the population in that year, what is the probability that a person would be under 65? So first you need to add, so you need to find the total. You don't know what the total number is, but you can add the 56 million plus the 275.6 million. So what I'm going to do is I'm going to go ahead and project my calculate 84. So let's go ahead and pull out our calculator. Let me share my screen as my calculator should be opening up. And then hopefully I don't get any ads. So then we're gonna go ahead and put in 56.052. They're both in millions plus 275.618. These represents million. Hit enter. So my total number of people that I have in the US is 331.67 million people. And then the number of that you're looking for is, we are going to be selecting randomly a population who is under 65. So who's under 65? The 275, the 275.618. So let's go ahead and divide 275.618 divided by, I'm going to put a parentheses here, and 331.67. Remember, these are all millions. And that's going to give me roughly 0.831 million. That's the number of chances. So let me go back to my screen. So we're looking for the probability under 65. That's the number under 65. That's 275.618 million divided by the total. And there's a typo here because it's 56.0 56.052. There is a typo right there. Let's fix that. And that's going to give us 0.31 million. So if you're randomly selected, that's the probability. Okay, 0.831 million. Let's talk about now the definition of the law of large numbers. So as an experiment is as an experiment is repeated more and more times, The proportion of outcomes favorable to any particular event will tend to come closer and closer to the theoretical probability. So, when you do an experimental probability, if you repeat it, the many times you repeat it, it's going to take you closer and closer to your theoretical probability. That is the definition. Let's look at comparing the differences between empirical and theoretical. A series of repeated experiments provides an empirical probability for an event, which by inductive reasoning is an estimate of the event's theoretical probability. When you increase the number of repetitions, it increases the reliability of the estimate. Likewise, an established theoretical probability for an event enable us to use deductive reasoning. One is using deductive, the other one is inductive. So empirical is inductive probability or inductive reasoning. Here we use deductive. To predict the proportions of times the event will occur in a series of repeated experiments. The prediction should be more accurate for large numbers of repetition. Okay, so the big difference is one uses inductive reasoning, the other one uses deductive reasoning. Empirical, the experimental, we're actually performing the event, whereas a theoretical is a very close approximation of what we're thinking. Let's look at the probabilities in a genetic. So probabilities in genetic, Gregor Mendel and an Austrian monk used the idea of randomness to establish the study of genetics. So this is an application of probability. So probability is used all the time. Gregor Mendel, an Austrian monk, used the idea of randomness to establish the study of genetics. To study the flower color of certain pea plants, he found that pure red crosses with pure white produces a red. So let's say you have a pure red and it's mixed with a pure white. It will still produce a red. Mendel theorized that the red is the dominant. So what he did is he symbolized it by the large R, and the white, which is the recessive, he symbolizes as little r. The pure red parent only carried genes for red R, and the pure white parent only carried genes for white. So what we're going to do is have a representation. Big R represents the red color. Little r represents the white color. So we know that this big R is the dominant gene. Because when the pure red crosses with the pure white, it produces a red. So that means that red is the more dominant. So hopefully we learned that back in our first biology class when we were talking about recessive and dominant genes. Looking for every offspring. So this next example is the carry-on for this one. The probability in genes, every offspring gives one gene from each parent, which leads to the tables below. Every second generation is a red because R is dominant. So let's look at this one. We have the first parent and the second parent, and this is the offspring. So we're going to create a table where I have R, R, little r, little r. So if we combine, so we're doing like a product table, R and R gives us R, little r, little r. They all have R and little r. Remember that R is the dominant. So then the dominant gene. So then when you mix an R, a red with a white, you will get a red. So then that tells us then the second parent, the second and third generation, we will have the first parent, R little r. The second one will be R little r. So the first would be RR, there it is, R, little r, little r and r, this still produces red. And look at the last one, RR, that is pure white. 1 out of 4 whites right here. So we have the first to second generation, and then we have the second to the third generation. Let's say that the first parent was red. So you have a mixture, see how you have R, R, big R, big R, big R, there it is. And then on this side, you have big R and little r. You do create a product table here, and we answer the questions that we have. So referring to the second and third probability table, so we're looking at this table now. On the previous slide, determine the probability that the third generation will be red. Well, let's look at what gives you red. Big R and little r. How many do you have? You have 1, 2, 3. Well, and okay, so you have 2 of those. So this will give you a red. And RR will also give you a red. So how many do you have? You have 1, 2, 3 of those. So 3 out of 4 would be your probability of getting a red. The probability of getting a red on the second to third generation is 3/4 or 75%. Of getting a white, that's when you get the little RR, and that's the probability of getting a white. And that is 1 out of 4. So based on the probability of the sample space, here it is, it's equally likely. You have R, 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 big R, little R, big R. So all these 3 times it gives you your red, and only this time it gives you your white. So 3 out of 4 and 1 out of 4. So there it is. Probability of getting a red, 3/4, and only one combination, 2 little R's will give you a white. So that is only 1 out of 4 chances. Okay. Let's talk about next is odds. So odds, it's an extension of probability. And we have 2 types of odds, odds against and odds in favor. So let's first talk about the definition. When you're looking at odds, odds compare the number of favorable outcomes to the unfavorable outcomes. Odds are commonly quoted in horse ratings, lottery, and other gambling situations. So you have odds in favor of winning and odds in favor of losing. In all outcomes in a sample space are equally likely. A of them are favorable to the event E, and B of them are unfavorable. The odds in favor of E are A to B. So A to B are the odds in favor. And it looks like this. A to B or B to A are the odds against. So right now, we're not looking at the sample space, but how many are against and how many are them in favor, and who's going to win? Which one has a higher chance? Which one has a higher probability? Odds of favor and odds against. Let's look at the example of finding odds of winning. 200 tickets were sold from drawing to win a new television. If you purchase 10 tickets, what are the odds in favor of you winning? Okay, well, there is 200 number total and you bought 10. The odds in favor, well, you have to do 200 minus 10, 190. So there are 10 out of 190 choices that are going to be in favor. So this is A, this is B, because you're subtracting the odds in favor to the total number of values. So you have 10 chances to win and 190 chances to lose. Then you have 10 out of 190 in favor. Now you can always reduce 10 and 190. They're both divisible by 10. 1 out of 19 chances of winning. Which is not that high. Now, what if you're converting them from probability to odds? So let's say this. Suppose that the probability of raining today is 43. Give it in terms of odds. So the total number of probability is 100. If you remove 43, it's going to give me 57%. So that tells me that you have 57 against 243. So we have the probability of getting a rain is 0.43, or 43 out of 100. So 43 out of 100 are favorable. So what is unfavorable? The 57%. So 43% will be in favor, whereas 57 will be against. So the odds in favor of rain are 43 to 57. So these are the odds in favor, the odds against. So it is 43 to 57. So you're going to first use the definition of a probability, and then you're going to subtract it by the total outcome. You're going to get 57 against. So all you have to do is 43 in favor, 57 against. A to B. Again, you're looking for the ones in favor. That's what we've been doing so far. Now, how do we convert from odds to probability? Now, your odds of completing a college algebra is 16 to 9. What is the probability that you will complete the class? So 16 to 9, this is the odds in favor. This is the odds against. So you need to add the sample space, 16 plus 9, you get 25. 16 of them is your passing. So you're going to get 16 out of 25, which is 64%. So you have 16 favorable outcomes, 9 unfavorable. You have to sum both the odds in favor and odds against. You need to sum the odds in favor, the odds against, and that will give you your sample space. And then you apply the formula of probability of completion, which is 16 out of 25, which gives us 64%. Now, that's the end of the lecture. However, what if I wanted to do the other way around? So if I'm looking for the odds against, so let's look at number 10, finding the odds of winning a TV. Well, instead of being 10 of 190, now you would just flip them around, 190 to 10, 19 to 1, losing. This is against. So flipping them around will give you the solution. Same thing here. What is the probability of not raining? The probability of not raining will be 57%. In this case, 57 to 43. It's backwards. So the odds against, there it is. And here are the odds in favor. 57 to 43, 43 to 57. Same thing here. What is the probability of you not completing the class? So the probability of not completing the class are the odds against. So then now you have 9 to 16. You still add them, you get 25 out of 9, which is going to give you what percent? It's going to give you 36%. And that would be the odds against. So you can always go back and forth between odds against and odds in favor. And that will be the end of lecture 11.1. Thank you, and I will see you in the next recording. Bye.